BME 306 Python tutorial. My name is Barrett, and in this video we'll be running through a primer on the Python language with some focus on image processing. This tutorial is not going to be a complete course in any way on Python, but will help get you set up with some basic concepts so that you can take off running with your own projects. So in this video, I'll be working in Spider, which is a fully integrated development environment you can download from anaconda.com. But this is definitely not the only IDE to work in. Online, you could just as easily follow this tutorial in a Jupyter Notebook or a Google Colab file. Each are excellent online resources for coding in Python. But with that said, let's get started. So I'm going to open up my IDE here. And as I'm walking through this video, I just want to say at the top, I won't be adhering to proper code formatting guidelines. So just beware if I'm importing functions in the middle of the script, why I'm doing that and why we're going to be using probably an excessive number of print statements. Now, with that said, let me outline what we're going to walk through, starting with print statements, before moving on to how you define variables in Python, list objects, the Numpy library, loops, plotting, and then some basic image processing. So any decent code tutorial always starts with a hello world script. So we're going to write ours now. And as you see pop up in my console, we print out hello world. Python makes it just as easy to include numbers in print scripts. So we could say 2 plus 2 is equal to 4 and run that. We see that pops out as well. And you can also do mathematical operations within your print statements. So if we were to say something along the lines of 2 to the 23rd is equal to 2 to the 23rd, we see the appropriate number pop out. So these are pretty self-explanatory, and we're not going to spend any more time on those, but there's your introductory hello world. The next thing we're going to talk about are variable definitions in Python. So just like any other language out there, you can write something to the effect of a is equal to 10. No need for semicolons. You can also, on one line, define a variable is equal to the result of some mathematical operation. Or you can define multiple variables on one line with a comma. So you could say C, comma, D is equal to big 10. And we can print these to show that that's indeed what we got. And as we'd expect, A is equal to 10, B is equal to 20, C is equal to big, and D is equal to 10. As we're going from section to section, I'm also going to comment out previous ones so that we don't have all this mess in the console. But that is how you would define a variable in Python. Pretty straightforward. Next up, we're going to talk about the list objects in Python. So similar to how cells would work in MATLAB, if you're familiar with that, we can write out, actually, I'll just comment out the print statements so we can keep those variables in play. Python lets you define lists as such within square brackets. And lists can be a collection of any kind of data type. So here I'm showing our list E is equal to 2 integers, and a string are big. So you can also just define them as a collection of numbers. So we could say E is equal to 10, 20, 30, and we'll print E again. And we see that we can redefine the variable and change out big with the number 30. So that's great. The other thing you can do with lists is you can use them to pre-allocate space. So I'm going to define a new one, F. And I'm going to make it repeat the number 1 10 times over. So print F now. And we see that we end up with 10 ones in a list type object. To verify the length of that, we can also just type len, F, like you would the term length in MATLAB, and we see that it's 10 objects long. Next up, we're going to talk about how you would index within an array or within a list. So within Python, it's 0 indexed, so we start from 0. And from our list F, which is currently just all ones, we'll take the first element, we'll set that equal to, say, 5, and we can take the last element and set that to 10. So we'll just print F one more time, and we see that the first element's 5, last element's 10. Python makes it pretty easy to just go from there. So if we wanted to get the second element, we would write F1, 2, 3, etc. And working backwards, you would type either -1 for the last element, -2 for the second to last, -3 for the third to last, etc. So just as a proof concept, we'll say the second to last element is 6. And that's exactly what we'd expect to see. So I'm going to comment out these print statements. And then we can move on to another concept, Numpy arrays. So oftentimes in scientific computing, we'll want to do some sort of mathematical operation on a list or an array, but you'll find that with lists like we were working with here, if I were to say try to subtract the number 1 or the number 2 from our list F, so F is equal to F minus 2, when we run that, we end up with an error that you have an unsupported operand types for negative, same thing for plus, list, and integer. That's because you can't do mathematical operations on lists in Python, which brings us to the Numpy library. So Numpy stands for Numerical Python, and it lets us do something pretty cool. So we can say, actually, let's import that library first. In Python, you import libraries by saying import, the name of it, and then you can say what you'd like to call it by typing as, and then what you're going to refer to it within your script with. So I'm going to import NumPy, and I'm going to call it NP. Python is object-oriented, so to call any definition within that library, you would just type np dot, and then the name of a function. So we're going to take our list F from before, and we're going to cast it as an array, and then try printing it again. And what we'll see now is looks really similar to before. We have all the same elements, same order and value, but now if we're to try and define F as itself minus 2, we can actually do that mathematical operation. We can also do multiplication, division, and on with a NumPy array object. I'm also going to open my variable explorer here so you can kind of see these variables as I'm going through what their type is, size, and their value. Next up, we're going to work with the NumPy ones function. So what this does is it defines either a vector, matrix, or a tensor of some value, or of some shape, and the entire matrix will just be ones. So we'll say G is equal to np.ones 5, and we'll see that when we print that, we end up with a vector of 5 ones. This is really similar to some MATLAB commands. We can also do mathematical operations on that, just on the line where we're defining it. So we could say np.ones length 5 times 3.1. And now we end up with a vector of 5 elements, each 3.1. Equivalently, you can write, say, G is equal to np zeros of 5. And when we run that, we'll see that now you have 5 zeros. Pretty straightforward stuff. Now what's interesting is when we get to using those to define matrices. So like I was saying earlier, I'll take a new variable h, set that to np1s of 5, 5. Now I'll just multiply that. I won't multiply that for anything by anything for right now. So printing H, we see that now we have a matrix of ones that is 5 rows by 5 columns. This could also be 10 rows by 5 columns, or vice versa. Or it could also be multi-dimensional if we wanted to have it, say, 10 by 5 by 2. That's a little outside the scope of what we're going to do today, though. So for now, we'll just leave that as matrix 5 by 5. Like with the vector definition before, we can also predefine all the values in that. Say we'll multiply by 25, and when we print that, now we have a matrix of all 25s. And then similarly, we could say H2. We'll set up a new variable, could be equal to NP zeros. And if we wanted that to be the same shape as H, we could just type np.shape H. And we'll try printing that. And we see now we have a matrix of 25s and a matrix of zeros. Matrices are a lot cooler than lists, partly because of those mathematical operations we were talking about before. So some examples of that, if we wanted to say, write out H2 minus H, we can do that. We can also write out H times H2, and running this, pretty evidently, if you're multiplying by zeros, you'll get zeros. But we could also say set the first and last column of our H2 array or H2 matrix to some value. So in Python to do that, where previously we were talking about using grabbing the element by saying 0 for the first element or -1 for the last one, in a two-dimensional setup, you could write colon comma 0. We'll set that equal to 1, or colon comma -1 is equal to 10. Now print H2 one more time. And what you see is the colon operator just says for every row at the 0th column, set that equal to 1. And the second line that we defined, H2 colon -1, says at every row in the last column, set that value equal to 10. And now if we were to write H times H2, what we'll find is the first and the last columns are multiplied together, and you end up with 25s and 250s. So just like we'd expect, and pretty great start. So more generally, you could also write np.multiply H and H2, but that's really only if you're using a matrix definition. So like np.matrix H2. But you lose out on some of the generality of NP1s and NP0s like we were working with here. So we're not going to work with matrices explicitly defined as such. And we'll just stick with this notation here, which is an equivalent element-wise multiplication. Next up, let's talk about loops. So in Python, loops are done pretty easily. You can say, we're just going to run through for loops today. So we'll say for I in range 10, colon, print I. Let me comment out those print statements from the previous section. And so for I in range 10, print I. And what we see is we print out starting from 0 all the way up to 10 elements later at 9. You can equivalently write a loop as for I in range, say, 1 to 11, print I, or for 11 to 1, working your way down. 11 to 9. So just like we'd expect. The other neat thing you can do with loops, though, that is pretty unique to Python. There's ways to do this in other languages, but Python's really amenable to it, is if we had, say, a list, like before, of strings, not something that you would intuitively think of for iterating through, but let's say that we define a list, we'll call it list 1, of just some nouns or verbs, whatever you want. We can now write for I in list 1, print I. And running through that, you'll print every single element in your list. So this can be pretty useful, say if you were to have a time range, t range, we can set that to a NumPy object linspace. I'll have that go from 0 to 10 for I in t range, print I. And we would go through each one of those elements in our t range object. Comment that out and come back to the list 1 for now, though, to show how for I in list 1, you can not only print out each element, but you could also say for idx comma I and enumerate list 1, print idx and I. And this lets you grab the index associated with each one of those objects in your list. So if you've ever written something that looks kind of like this, you have a counter, and then in your for loop you might write counter is equal to counter plus 1. This is just a really quick and easy way to get around that without having to explicitly define any dummy variables. So that just about covers it for loops. One last thing that you might use is, let's say that you're working with, we'll comment back in that time range variable. Let's say we're going from sometime 1 to 100. We have, or 1 to 1,000. And we have 1,000 different elements in there. 1,001. We could say for I in t range, we could print that out, but you would just have a lot cluttering up your terminal or your console. So one way to get around this is you could just write if I modulus 100 equals 0, then print whatever the value is. And then we really pare that down. So this is an example of a conditional statement in Python. You would just write if whatever your conditional statement is, colon, and then indent for whatever operations you want to run. No need for an end statement, or anything similar. As long as you're tabbed in, Python will run whatever's under the conditional statement. So we could say print I, and then separately, some other operation. So great, that wraps it up for for loops. Now let's get into plotting. So to work here, we're going to import matplotlib.pyplot as plt. Bit of a mouthful, but this is just a library that allows us to do plotting similar to MATLAB. So I'm going to grab that time range variable again and drop it into this section. I'm going to comment out the previous section. And I'm going to say plt.plot time range, and then time range squared. And when we run this, we end up with a plot that pops up on us, and we can see that as time range goes linearly from 0 to 1,000 on the x-axis, its square creeps up along the y-axis. We can label these by saying plt.xlabel time and plt.ylabel f of t. You can also write a title by saying plt.title. And running this, great. We end up with x, y, and title labels. Yeah, nothing much more on that. You'll notice that I use semicolons when defining out those labels. This is equivalent to just writing out those three on their individual lines. But if you want to maybe save space, or you've got really short functions like that, you can put them all in the same line and separate them with a semicolon. You can also, so if we want to make a new figure, we just write plt.figure. And that breaks us into a new figure pane. And say if we wanted to do a scatter plot, instead of saying plt.plot, we would just write plt.scatter. And we'll plot something slightly different. So instead of the square of time range, we'll take the square root. And yeah, just like we'd expect. So one last thing for plotting that might be useful. Actually, two last things. One, you'll notice that neither of these plots disappeared after I ran them. We can remedy that by just including a plt.closeAll command at the top of our script. The other thing is, say if you wanted to plot multiple images on the same axis or in the same window, we'll say plt.figure, make a new figure, and then we can write plt.subplot 2 on 1. So we have two different subplots, and at the first row and first column, we will plot just like we did before our square function, and then we can say plt.subplot 2 on 2. So a subplot with two panes in the first row and second column. And we'll define that as equal to our scatter plot. And when we run this, we see what we get, both of them within the same window. And so that does it for plotting, at least for the most part. I'm going to keep the import matplot lib command as well as the plt.closeAll command because we're going to be making a couple more plots in the next section, in our last section, image processing. So previously, before starting this tutorial, I went through and I downloaded a couple of images from the web. We've got a sneaker, a shot of LA, the US flag, and some cells. I'll just go through a couple of different operations we can do on each of those to show how to manipulate images. So the first thing that I'm going to do is import that sneaker. We'll call it vans is equal to plt.imread, vans.png. So the string here describes whatever image I'm trying to import. If this was in a folder, I would just write the relative path to it, but because it's in the same space as this file, I can just write vans.png. What imread does is it reads in that image to a Python object, which we can then play around with. So I'm going to write vans equal plt.imread, and then define a new figure, and then say plt.imshow vans. So I'm going to read it in and then display it back. Now, if we go to our variable explorer, we can see that vans has an X and a Y dimension, as well as 4 channels on it. Those represent the red, green, blue, and alpha channels. PNGs, unlike JPEGs and other images, have an alpha channel which sets transparency. And we're going to get into that right now. So I'm going to define another figure to kind of illustrate what I'm talking about. And we'll say subplot 141 plt.imshow vans, and I'm going to have this plot at every row and every column, the value at the 0th axis. So this would be our red channel. I'm going to have it plot with some color map called reds, which is just a Python native, which colors your graph red. We're going to do a similar thing for the blue, green, and alpha channels by saying greens, blues, and I'm going to leave this last one blank. So when we plot that, we'll see what our original image, shown on the left here, looks like when we break it apart into its red channel, green channel, and blue channel. This last pane shows the transparency values. So here in the yellow region, you'll note down around where my mouse is now that transparency is set to, or rather I suppose opacity is set to 1 where we have the image shown, and then around it it's set to 0 so that the background is removed. Now if we want to mess around with some of those color channels, say if we want to remove red content, we could define some variable, we'll call it low red. We'll say that's equal to vans at every row and every column on the 0th channel, so the red channel. Low red is equal to every pixel where the red value is greater than 0.5. And then we can use that to index every single one of those values and say that vans low red on the 0th channel is equal to 0.5. And in so doing, we're going to cap the max red value to 0.5. So we're going to do another plt.figure, plt.imshow. And now when we plot this, we see that what was originally a pink and white image turns into a sort of green and gray image by removing a lot of the red content. So that's a basic primer on importing an image and messing with its color channels. Now what we're going to do is a little bit more involved image processing method, and we're going to do some convolution. Specifically, we're going to be blurring an image. So for this one, I'm going to import that photo of Los Angeles. I'm going to say plt.imread la.jpg, and we'll just show that like we did with the sneaker from before. Great. So we can see we have a pretty large image of Los Angeles, about 3,500 by 2,000 pixels. So we can really zoom in and see some of the details going on along the skyline and in the foreground. What I'm going to do is first convert that image into a kind of grayscale. Making a proper grayscale image isn't exactly as simple as I'm making this. What I'm saying here is just to take the average value at every pixel across the red, blue, and green channels. But it'll work for our purposes. So now I've got that. I'll show that one more time. It'll set our color map equal to gray, so Python knows how to visualize it. Cool. So color image on the left, grayscale image on the right. Resolution, still the same, but now the color content is slightly different. So I said that we're going to be doing a convolution of sorts. And to do that, I'm going to import from SciPy n-dimensional image the function convolve. So from scipy.ndImage import convolve. I'm also going to define a kernel. We'll call it the blur kernel. And I'll set that equal to a NumPy array of 1 divided by 16, 1 divided by 8, 1 divided by 16. If it looks like I'm making this up as I'm going, it's not quite that simple. The kernel I'm defining here is actually a standard one for doing Gaussian blurring. And what it allows us to do is say for I in range 10, actually, what it allows us to do is this. LA is equal to MP is equal to convolve LA blur kernel. It allows us to slightly blur the details or round out any rough edges on the original image. Now, if we just run it the one time, it's not that apparent of an effect, but if we were to say in a for loop, write for I in range 0 to 10, do that convolution repeatedly, what we'll find is the blurring effect becomes, over time, much more noticeable. Zooming in here on the City National Bank, and you can see that only after 10 iterations of this, we can hardly make out the letters. Now, another thing that we can do is to check how, over time, the change in image resolution happens. One way to do this is by taking the L2 norm of the change in the image. So what I mean by that is we'll say, we'll pre-allocate an array. We'll say L2 is equal to 0, comma, times 10. And then for I, for IDXJ and enumerate range 10, we'll make that a little bit simpler. We're going to do our operation from before, but we're also, you know what, I made that just overly complicated. We'll keep it for I is equal to, or for I in range 10. We'll say L2 of I is equal to numpy linalg.norm of LA new minus LA. And we'll just define LA as the newly blurred image below that. And what this lets us do is say, in a new figure, plot our L2 over time. And we'll also give it an x-axis. So we'll say rounds is equal to pi a range 0 to 10. And once we run that, we'll see that with each round of blurring, we have an almost exponential drop-off in change from the previous blurring round to the next one, is the degree to which the image resolution drops off or gets eaten away. Now the last two examples that I'm going to work with, we're going to do some image segmentation or masking, where we pick out different colors of interest. So we'll comment out the previous section. In Python, I should note, you can do block comments with triple quotes and single line comments with the pound sign. For the next one, I'm going to import photo of the US flag, which is a PNG. And just like we did before, we'll show it just to make sure that everything got imported correctly. Run. Looks good. And what we're going to try to do is break out the blue region from the red region from the white region. And looking at this, it seems that, again, if you look down here along the bottom of this figure explorer, the white region is unitary 1. So the red, blue, and green channel are all 1s. Whereas the red channel, or the red stripes, are slightly off. The red seems to have a lower bound of around, we'll say 0.65. And the blue content on that, we'll say that has, I don't know, an upper bound of about 0.5. We'll just be really conservative. 0.55. And on the blue side, I'm looking at these really for where the edge cases are. A lot of images will blur along color boundaries. So you see the red's pretty consistent here until I get to this region in between the red stripe and the white stripe. But the blue one seems to have an upper bound for its red content around 0.7 and a lower bound for the blue content around, we'll just say 0.25. So what we can do is now go through and define our different regions. So white, red, and blue. I'm going to start with white just because that seems to be the simplest. We'll say white is equal to MP all, where every channel for a pixel in our image, we'll say everywhere where that's greater than, I don't know, 0.7. We'll define that as the white region. And we can do a similar thing for our red content. So everywhere where, MP all probably won't be the best way to go about this. So what instead I'm going to do is say MP logical and everywhere the red content in the flag is greater than 0.65, and as well as everywhere where the blue content is less than 0.55. So to just kind of walk through this line a little bit more, we're saying that the red region, so our red stripes here, are every one of the pixels where the red channel's intensity is above 0.65 and the blue channel's intensity is below 0.55. And I'm going to copy paste that line for the red definition into the blue one and say that's equal to, instead of where the red content's greater than 0.655, say where it's lower than 0.7, and the blue content is greater than a quarter. So I'll take that and we'll do another subplot, or another subplotted image where we start with just flag. And then we'll say everywhere we have red, everywhere we have white, and everywhere we have blue. I'm also going to attach titles onto each one of those just so that we can keep them straight. And when we run that, we see that the red region segmented out here in yellow, the white region in yellow, and the blue region in the blue field. Because that can be a little bit tricky to do though, and we only have 3 colors, if you've got 2 of them already defined, like we do for white and red, I could have just as easily written blue as, say, MP logical and everywhere where the image wasn't red and everywhere where the image wasn't white. I'll comment this out, and what we'll see is when we run that, we wind up at the same result, where the blue region is really easily segmented out from the rest of the colors. And to verify that we don't have any straggling boundaries left over, we'll define a new figure, and we'll just say plt.imshow red plus white plus blue. And what we see is nothing. The reason being that the whole field is of uniform intensity. Now, you might be questioning the purpose of segmenting out an image like this, so I'll leave you with one final example of applying this to more of a biological case. We're going to take a slide of some onion cells that have had their nuclei stained, and we'll try to pick out those nuclei. So I'm going to import the image onion.png, same rigmarole from before, plt.figure, imshow onion, and great. We see our cell, we've got our cell walls, and our nuclei stained in this kind of bluish color, bluish purple color. Zooming around this, the red content looks like it's above 0.5, roundabout, or the red content, pardon me, looks to be below 0.5, and the blue content is above 0.5 at each one of these nuclei I'm hovering over. So to just really quickly grab those, we're going to do what we did with the flag example and say nuclei is equal to MP logical and where the onion at every row and column, the red channel is less than 0.5, and at every point along the blue channel is greater than 0.5. I'll use a color map, blues again. Run that, and we see that we've got a pretty good idea of where each one of those nuclei are without any cell walls in the way. If we want to get a little bit fancier, we could also use like a median filter to kind of pick out some of that salt and pepper noise. And maybe get a better idea of where each one of those nuclei are. And just a couple of lines, you can see that we're pretty well halfway there to a nuclei detector or a cell counter. But I think that should give you all a pretty good basis on maybe some basic Python operations as well as image processing techniques for region masking and blurring, convolution, those sorts of things. And in future videos, we'll talk more about how you might implement your own system of ordinary differential equations. But for now, this concludes our tutorial on basic Python for BME 306. Thanks for your attention, and best of luck with your semesters.